First of all, do you see my screen properly?
Yes, perfect.
Oh, okay, good. So, hi, my name is Vedad Hadzic. I am a PhD student at the IAK Institute of the Technical University in Graz. And today I'm going to present mine and my colleagues' work on masking verification in particular for hardware, and then we show how we can port this into the software realm. So yeah, the work that I'm going to present was done. So this work on Rebecca was done by Rinat Yusupov mostly, and I did a follow-up called Coco Alma, which is like a more advanced version of the same verification principle. So I'm first going to go over like how it works and what the target is and so on, and then I'm going to show you some of the really nice results that we achieved. So power analysis attacks. So as most of you know, power analysis attacks are one of the big problems when you design integrated circuits. So a malicious party could measure the power consumption of your circuit at a specific point and then be able to correlate this to values that might have something to do with the secrets that you're processing. So power analysis attacks work in a few simple steps. So first you put a probe on a chip at some point which you want to measure. You measure the power, then you do a bunch of math, which is essentially like a correlation attack. You try to correlate the power traces that you see with secrets that you know beforehand or plain texts and so on. And then you try to make a distinguisher and like reverse engineer an unknown key, for example. And if something like this is possible, then there's like a big question of how can we protect against this in hardware, especially. So something that people came up with is masking. And masking is a relatively simple principle which just says, okay, if I have no idea what I'm computing, then an attacker cannot know what I'm computing either. And this is achieved by splitting information into several parts. So in the most simple case that I have depicted here, a piece of information X, for example, is split into two parts, X0 and X1. And the original value is just a linear combination of these two. And the same goes for everything that, so for all the inputs of the circuit and for all the intermediate values. And this is rather straightforward. So what you do is when you want to do an XOR operation, for example, you just XOR the parts separately to get a representation of the result. And if you want to do any nonlinear Boolean function, for example, an AND gate, you have to introduce some randomness and then compute a much larger expression. So in the end, the amount of computations that you need to do increases rather significantly, but you somehow guarantee that for each of the gates in your whole design, an attacker that is able to not just get the power trace, but to get the exact value of this gate cannot correlate it to anything that has something to do with the secrets. Because like take just the inputs, for example. If an attacker is able to obtain the value x0, then they cannot deduce what the value of x is because it depends on the value of x1, which is unknown. And using x1, we can change the value of x to anything independent of x0. So there is also like a big effort in the community that develops these masking protection schemes to reduce the number of randomness, because as you might know, the amount of entropy that you have in a circuit is kind of limited, so you cannot sample it forever and expect it to be secure. And you want to reduce several other like development aspects. So you want to have low latency, glitch resistance, and so on. So what I've shown here is actually like the Boolean masking scheme, which is broken in hardware because it, like if you have a glitch on one of these signals, then you still get a value that's correlatable to one of the, in this case, inputs. So this has to be protected with like additional synchronization layers of flip-flops and so on, but this is the general idea. So what we're actually trying to do when we do power analysis, and in this case, if we look at the probing model for that models power analysis, an attacker can pick one value inside of the circuit where they learn the exact value of this throughout the whole computation. So for example, if we have like a function that computes like A and B XOR C, then the attacker would only learn the result of this and would try to kind of deduce something about the inputs. And this is in many cases actually possible. So in this case, the attacker knows that A strongly correlates with the actual result of this function, because if this function returns like a 1, if it returns high, so it's true, it means that A must have also been true. And if it returns false, then we know with like a 66% chance that A was also false. So this gives the attacker a tool of kind of measuring multiple values at the same time by only observing a function that computes using them. And the same arguments can be done for the other variables except for B and C. And B and C do not correlate by themselves to the output of this function, and can therefore be like 50% of the time it's going to be false and 50% of the time it's going to be true. So the question is, why is this useful? Because it shows dependence. So if the attacker is able to measure the value of one specific gate in the design, then we can kind of know what are all the things that he learns. The way that I computed it in this example is by just looking at the truth table of this function, which is super inefficient, as you might know, because like the size of the truth table is exponential. And as always, there is a better way of doing this. So what Renat and Roderick, which was his supervisor and is now my supervisor, came up with is to use a really old trick that Fourier did, which is look at these Boolean computations as integers. Specifically, transform the domain of the truth values into -1 and 1. So balanced Boolean, it's called. So then you get these nice properties that an XOR is just like multiplication, and nonlinear operations are always going to be made up of these like 4 terms, where one of them is a constant, and then you have both inputs, and then you have like the XOR of the 2 inputs. So, and the nice thing about this is that it works recursively, right? Because you can just compute this and then like use this as a building block in the next computation. So in this case, for the function that we have seen previously, you get 1/2 plus 1/2 A plus 1/2 BC plus minus 1/2 ABC. And from here, you can directly read what the correlations of this are. So it correlates to the constant false. It correlates to the value of A. It correlates to the XOR of B and C. And it correlates to the XOR of A, B, and C. In this case, it correlates negatively. So if the function outputs true, then it's much more likely that A XOR B XOR C is going to be false, for example. So one thing about this, which is also really bad, is that you can have exponentially many of these terms. Like you're just replacing one exponential thing with another exponential thing, which is always bad. So you just what you just did is write down the same thing in 2 different ways, and you can actually show that it's equivalent. So what they came up with Rebecca is they came up with an over-approximation. And this over-approximation is rather simple. the over approximation just throws away all of these coefficients. So you do not track what the exact coefficient is for each of these terms. So you just say, I don't care. And instead, you only like detect whether the coefficient is 0 or not. And in this case, when you have an XOR, for example, what the in this case propagation rule it's called. What the propagation rule for this is that you take all the values of the first set of correlations and all the values of the second set of correlations, and you multiply them all together. So you do a product between two sets. And what you end up with in this case is xy, which is exactly the only term that had a non-zero coefficient for x or y. And for the AND gate, it's similar. In this case, I use a simplified notation here, which just says that that you like add the constant false or 1 in this case. So you do this multiplication, and then you end up with a set that also has all the elements that the thing should correlate against and none of the others. So this can be, again, computed recursively, as I show in this example below, where you have bx or c is bc. And then if you do the same step as above for the AND gate, you get the elements 1a, b, c, and a, b, c. So it correlates against the constant, against a, against bx or c, and against the XOR of all three variables. So this seems really useful until you remember that, again, this whole thing is exponential. So what you did again was you threw away the constants that you had at each term, but you didn't gain anything. So the representation is still exponential. So you need to check exponentially many terms, whether any of them correlate to one of your secrets. And this is where a clever trick comes in, which they did, was to represent all of these as satisfiable solutions to a formula. And I'm just going to illustrate here how this works. So you take each of these variables and you give it like one propositional variable per element in your circuit, so per input and per gate. And you like add equations into the SAT solver in this case that make only those assignments satisfiable which correspond to a valid set representation. And in this case, like for inputs, you just say that the input itself is the only active variable in there. And for example, I show here a z, which is the end of x and y. And you have to do something more complicated. But what you end up with is seen on the right side. So any satisfiable solution to this problem that you give to the SAT solver is going to have a valid px and py that look like this. So x is going to be true and y is going to be false for the first node, which means that like x is in the set. And for the second one, so for y, you're going to have x is false and y is true, which is the set for y. And for z, you actually have 4 different solutions which all work out. And they represent the four elements of this correlation set that we have found previously. So all combinations of x and y are in this case satisfiable. So if both are false, we see that it's a constant. If one of them is true, then we see that it's the variable that's true. And if both of them are true, then it means that the thing correlates against the XOR. And you might think, okay, again, I replaced something that was exponential with something else that's still exponential. But one thing that you need to like comprehend is that this is no longer exponential, because you're not going to iterate over all the possible solutions of this problem, but you're going to search for one specific solution. And the solution that you're going to be looking for is something that contains an XOR of 2 shares of the same secret. So if we have a secret A and the computation splits it into 2 parts, then you just try to find one assignment to all of these Boolean variables that are going to give you a correlation set that contains A0, XOR A1. And if the SAT solver is able to do that, then you have found an example where the masking was done incorrectly. And if you're not able to do that, then it means that the masking is correct. So there are a few downsides and upsides of this approach. So it only works for combinatorial circuits, so it has no idea about clock cycles. It does understand glitches and so on, but it has no idea about clock cycles. So you could not just copy-paste a simple design such as an AES implementation into this thing and have it work. So this is not possible. And it over-approximates because, as I have told you, that it ignores all of these coefficients, which means that you can produce cases in which these coefficients would cancel out after multiplication. And in like all the time I have worked on this, I have only seen it happen once. And it was in a really, really particular case where it was just set up right so that it would cancel in the real Fourier transformation and not in the over-approximation. So it disables this canceling and it can lead to false positives. But on the other hand, one of the upsides is that these false positives almost never occur. So and you can fix them really easily. So you can just add randomness into the circuit. So more randomness, one more random bit to disable this thing that you found. So you can fix these false positives really easily. And then I get to the second tool. So this was the first thing that we worked on. And the second thing that we worked on is this tool called Coco Alma. And it's called Coco because we used it initially for a co-design and co-verification approach of hardware and software simultaneously. And what I mean by this is going to be apparent in a second. So we did something like a BMC unrolling. So you unroll the circuit for each of the clock cycles, and then you build all of these correlation sets and put a bunch of optimizations on top of it so that it's able to handle like gigantic circuits of 20 or 30,000 gates and for like 200 clock cycles and solve the problem within like an hour. So what the basic approach is, you simulate the circuit execution, you get information about this particular run, and you generalize it for all the runs. So you extract control signals and so on. You compute these correlation sets and simplify them on the fly using the control signals. And then at the end, you test for a particular probing model for the masking security. So this is how all of these propagation rules look like. So in addition to what we had previously, so what I've shown you previously, we have this time component. So each of the sets is only valid for one clock cycle. And everything else stays pretty much the same, except that there's support for additional gates like multiplexers, and that there is a transient case. So everything I talked about previously is meant for the stable case, and this supports like this T sets are what is referred to as the transient case or glitches and transition leakage. So when you have a glitch, a simple XOR gate can have the same leakage as an AND gate or any other nonlinear gate because it can, depending on the speed of the signals, it can forward the first one or the second one or the XOR or just a constant. So this is something that we incorporate in this as well. And this, we use all of this. So the goal with all of this was take a CPU and run masking in software on it to show how powerful this approach is. So you take a full CPU design as a netlist. You take a program that you have written in assembly that does that implements a masking algorithm, and then verify this masking algorithm for the software on this particular CPU. And for this, like the main thing that was necessary are these runtime simplifications. And I'm just going to briefly go over what they mean. For example, if we have a control signal, in this case B, for which we know the value in each clock cycle, then we can, of course, simplify these correlation sets. So if in the nth clock cycle we have B is 1, and then we're going to have that X gets the value of A. So we just propagate the correlation sets for A to X. So we just say, okay, the correlation sets for X are equivalent to the correlation sets of A because B is 1, and the logic gate is going to propagate A. In the n+1 cycle, so in the next cycle, if B changes to 0, then we know that X must be 0, so it must be false. And we know that the only thing it's going to correlate to is a constant. Which means that we already can simplify, we can eliminate this propagation of A in this case. And for the n+2 clock cycle, it's the same. So B stays 0, and we see that the propagation stays the same. In the case of glitches, which is something much more interesting, we have similar behavior, but not exactly. For example, in the nth clock cycle, the value of A is propagated just like before. In the n+1 clock cycle, even though B changed its value to 0, there can be a glitch on B, which makes it it means that during the transition, depending on the speed of the B signal, it can be 1 or 0 in the same clock cycle. Meaning that there is a potential for the value of A to be forwarded through X. And this is exactly what we see here. So in the transient case, so for glitches, because B is a signal that changed its value, so it's unstable in this clock cycle, we can get a propagation of the transient correlation set of A into X. In the next clock cycle, where B continues to be 0, we know that there is no transition on B. And because it comes out of a register, we know that none of the previous signals have any influence. So there's not like one ancestor of B that's going to change and then cause fluctuations in the signal. So we know that B is stable, and it disallows this AND gate from propagating the value of A towards X. So even when glitches can happen, there is no glitch possible on B in this clock cycle transition from n+1 to n+2. And we know that X can never have the value of A, which means that it never gets the correlations that A has and only correlates to a constant. So this is this execution-aware simplification. And if you scale this up to a whole CPU, you're able to compute these correlation sets pretty efficiently, and ignore most of the stuff that has that never touches secrets pretty much. So as I said, we use this to find microarchitecture leakage on CPUs. We discovered a few wrong assumptions that a programmer might have about the leakage behavior of the CPU, and we found some leakage effects that were previously not explainable. And as I said, we use the full netlist of the CPU, and we find problems that can be fixed either in hardware or in software. So these are two examples of what we have found. So for example, if on a RISC-V machine, there is a move instruction, so you just store the value of x2 into x1, and these two are shares of the same secret, you can have leakage because in the brief transition period between when this is overwritten, you leak the Hamming weight of these of the overwrite in the power trace, which means that you essentially leak the secret. So this was something that was known before. Here is something that was not known before, and it heavily depends on the architecture of the CPU that you're working with, which is using shares in successive clock cycles. So if you have secret shares in x1 and x2, and then you do something benign with x1, and afterwards in the next instruction do something benign with x2, then you can still get leakage. And this happens because in the ALU, so in the register file, you have these output ports that go towards the ALU, and this gets overwritten as well. And because like x1 and x2 are the second argument, they appear on the B port of the register file. You overwrite it in the span of 1 clock cycle, which means that you leak the Hamming weight again. So this is again something that we found. We fixed a bunch of these bugs. So I don't know how much time I have left to talk about this.
Not much.
Okay, so we fixed a bunch of this. One big problem was the register file where things got combined even though you don't even use them. So this was really interesting. You can have like 2 shares of the same secret in the register file simultaneously, and independent of what you do, you would still get leakage. And this happens because of the multiplexer tree in the for the output ports of the ALU. And because the signals of the address can glitch that cause simply like completely independent stuff to leak together, which is really bad. So we fixed this. You can have the same problem in the memory, where we fixed it in a slightly different way to like not have to do a one-hot encoding over a really long memory space. We performed some experiments, so we were able to verify even something as complex as a 16 by 16 bit sliced AES box that takes like 1,900 cycles to compute and uses a bunch of fresh randomness and a bunch of secret shares. And we did all of this, like assuming that there are no glitches, you can do this within 20 minutes for a CPU that's like 20K gates. And for the case with glitches, it takes slightly longer. It takes like almost like 4 hours and 40 minutes or something. And we did this also for several other algorithms like the Ketchak S-Box and a bunch of famous AND gate implementations, and show that this stuff actually really scales well. Because previously, like with Rebecca, we were not even able to do a hardware implementation of an AES box with DOM masking protection within like 5 hours, and now we can do a full AES box 16 times simultaneously in a CPU that's 20K gates large. So yeah, it's more powerful than the other one. That's why I said it's on steroids. So now it's the time for questions, I think. And I need to like look at my clock.
We have time for 1, maybe 2 questions if we're quick.